Thanks, everyone. I'm Lynn Clark, and I make code cartoons. And I also work at Mozilla, where I'm in the emerging technologies group. So that's things like the Rust programming language and WebAssembly, which is a really fast way to run code that's not JavaScript in the browser and Node. And we also work on Servo, which is a new web engine. I'll be talking about all of these things today because they're all part of the future of the browser. So why talk about the future of the browser? Because browsers are facing a challenge. And whether or not browsers can meet this challenge could change the web as we know it. So what is this challenge? Browsers need to get faster. Content on the web has changed a lot since the early days of the web. In the early days of the web, speed really didn't matter too much. We were just looking at static documents. So as soon as that document was downloaded and rendered, it was pretty much done. The browser might need to do a little bit of work when the person scrolled, but nothing too complicated. Then people started pushing the boundaries. They started thinking, what can we do with this web besides just serving static documents? Pages started getting interactive. They started having animations. For example, do you remember when everybody went wild for drop-down menus and everybody was animating these slider things with jQuery? Once those were a part of the page, the web page wasn't just being rendered once for every interaction. With every change, it needed to be repainted. And sometimes, like when you had these drop-downs that were animating, the screen needed to be repainted multiple times for each one of those interactions. So for each change, for each interaction, there were multiple repaints. If you wanted interactions or animations to look smooth, these repaints needed to be happening at a certain rate. So the screen needed to be repainted 60 frames, 60 times per second. That meant that you only had 16 milliseconds to get all of the work done. Browsers made all sorts of changes to come up to speed, to accommodate the new applications and get up to that 60 frames per second. But as is the way with the web, content authors started pushing things even further. They started not just making their web applications more interactive, but bringing whole new classes of applications to the web, like PC games. And companies started talking about bringing things like Adobe's Photoshop to the web. These new classes of applications are taxing the web even more. And they're making it clear that things like JavaScript need to get faster. It's not just content authors that are pushing the boundaries of the web, though. It's also the hardware vendors. For example, the new iPad is going from 60 frames per second to 120 frames per second. And that means that the browser has half as much time to do just as much work. And new kinds of content are coming to the web and pushing this even more. For example, with VR, you have two different displays, one for each eye, and each of these has to be going at least 90 frames per second, or else the person could get motion sickness. Plus, each of these displays might be at 4K resolution, which means that you have lots more pixels in each display. Let's think about what this change means. If we're running a website on a 13-inch MacBook Pro, you have 16 milliseconds to fill in about 4.5 million pixels. With the next iPad, you have half as much time to fill in 3 million pixels. And with a VR experience, you have 11 milliseconds to fill in up to 16.5 million pixels. And this doesn't even include heavier JavaScript needs that you might have. That's a huge leap that browsers need to make in order to keep up. What happens if browsers don't keep up? Well, as more and more people buy these devices, as more and more content moves into these heavy applications, if browsers don't keep up, people will stop seeing the web as the default place to put their content. And this could mean that the web as we know it withers. And that's a pretty scary thought. But to be honest, I'm not too worried, and I'm confident that browsers can make this leap. The reason that I'm confident is because we've been prepping for this change for the past 10 years at Mozilla. We've been looking at the direction that computer hardware is going. We've been figuring out the new way that we need to program in order to keep up with these changes. The answer is parallelism. The future of the browser is parallel. We've only just started taking advantage of this in Firefox, but we're already seeing really big wins from it, and every indication is that this new way of doing things can get the browser where it needs to be. So in this talk, I want to explain exactly what the browser needs to do in order to make this leap. But before that, let's talk a little bit about what the browser actually does. So I'm going to start with the rendering engine, and that's the part that does the most important thing, which is going from HTML and CSS to pixels on the screen. It does this in 5 steps, but to make it simpler, I can split this up into 2 groups. The first group takes the HTML and CSS and figures out a plan. It figures out what the page should look like. So this is kind of like a blueprint. It says what goes on the screen, the widths, the heights, all of that stuff. The second group takes that plan and turns it into the pixels that you see on your screen. Now let's look more closely at each step in this process. The first step is called parsing. What the parser does is it turns the HTML into something that the browser can understand, because when this HTML comes in, it's just like one big long string of text. It's kind of like a big long paper ribbon that has all of these characters on it. But what we need is something different, something that the browser can actually use. A data structure that tells us what the different elements on the page are and how they're related to each other. I think of this kind of like a family tree. We need to turn this long paper ribbon into a family tree of the page. So what the parser does is it goes along this paper ribbon with a pair of scissors, and when it sees the opening tag for any HTML element, like a div, it cuts that out and puts that into the family tree. And then the next element that it encounters will go under that div. So let's say that the next element is a paragraph. That p tag will go under the div, and there will be a line between them indicating the parent-child relationship. So this family tree is called the DOM tree, or the Document Object Model. And it's called that because it provides a model of the document, which you can use to make any changes that you want to this document. So if JavaScript wants to change this page, if it wants to say, remove some of these paragraphs, it can just take them out, it can remove them from that family tree, and then they'll disappear from the screen. At the end of parsing, we have this family tree, the DOM tree. And that tells us about the structure of the page and these parent-child relationships. What it doesn't tell us is what all of these elements should look like. In order to figure out what they look like, we need to take the CSS that we've downloaded and figure out which styles apply to which elements in this tree. So that's the next step, CSS style computation. I think of CSS style computation like a person filling in a form for each one of these elements in the tree. And this form is going to say exactly what the element should look like. The form has more than 200 form fields in it. There's a form field for every single CSS property. And this form needs to be completely filled out for each element in the tree. For every element in the DOM, we need to have one of these forms that's been completely filled out. So at the end of CSS style computation, each element has its form. But there's still a little bit more that we need to figure out. We need to figure out how wide and how high things are going to be and where they'll be on the page. The next step, layout, takes care of this. It looks at the dimensions of the browser window, and from that, it calculates all of the relative values, like if a div is 50% of its parent. And it will also do things like break up paragraph elements into multiple elements, one for each line in the paragraph. And that way it knows how many lines high the box needs to be. The output of this step is another tree. In Firefox, we call it the frame tree, but in Chrome, they call it the render tree. I think that Edge calls it the box tree. But regardless what it's called, this is the ultimate plan. This is what tells us exactly what the page should look like. Now we move on to the next part of rendering, which is turning that plan into pixels. Now, filling in pixels can take a long time, especially when there are a lot of things rapidly changing on a page. Because of this, browsers have tried to find ways to reduce the work that they do and to make it faster. And one way that they've done this is by splitting up what gets shown in the screen into multiple different layers. Now, these are layers like you have in Photoshop, or I think of them like the layers that you have in an old-time animation, like the onion skin layers that they would have used to make cartoons like Bugs Bunny. You have the background on one layer, and then you have the characters on another layer. And that way, if the characters need to move, you don't need to repaint the background. The background layer can just stay the same, only the top layer needs to be repainted. So the first step in this process is called painting. That's where you create these layers. And the next step is called compositing. So that's where you take these layers and put them together, and then you basically take a picture of it and then send that to the screen. So that is how the page gets rendered. Now, I framed this as the way that a page's content goes from HTML and CSS to pixels. But what you might not know is that there's another part of the browser, the tabs, the URL bar, all of that stuff. And that part is actually separate. It's called the browser Chrome. In some browsers, such as Firefox, rendering browser Chrome is also handled by the rendering engine. So you have this rendering engine, and it has two different tasks. It has to render the inside of this window, which is called the content, and the outside, which is called the Chrome. And actually, it's not just two tasks, because for any tab that you have open, there's going to be a new content window. Even if the pixels aren't showing, because it's not the selected tab, it could still be running JavaScript. So the browser has multiple things it has to do, and they're all pretty independent of each other. And this is one of the earliest places where parallelism was introduced to the browser. In 2008, you started seeing a browser take advantage of new hardware to run these tasks independently of each other at the same time. But it wasn't us that did that. It was Chrome. When Chrome launched, its architecture was already using parallelism like this. It's called the multi-process architecture. And that's one reason why Chrome was faster and more responsive than Firefox was when it came out. Now, I feel like I should take a step back here and explain what this all really means, what the hardware change was that Chrome was taking advantage of, and what that change made possible. So let's do a little crash course in computers and how they work. You can think of a computer kind of like you think of a brain. There are different parts of this brain. There's the part that does the thinking. So that's addition, subtraction, any logical operations like and or. And then there's some short-term memory. These two are close together in the same part of the brain. Then there's long-term memory. Now, these different parts have names. The part that does the thinking, that's called the arithmetic and logic unit. And the short-term memory, those are called registers. And these two are grouped together pretty close to each other on something called the central processing unit, or the CPU. The long-term memory is called random access memory, or RAM. Now, in order to get this brain to do anything, we need to give it instructions. And the instructions are going to tell us what we need to do with some bit of short-term memory. So each box of short-term memory has a label so that we can refer to it, so that we can say what we need to do and what part of memory we need to use. Then we can use these labels in the instructions to say which values the instruction are acting on. For example, we could add a number to a value that is in short-term memory and get the result. Like we could add 1 to the value that's in register 4. One thing you may have figured out from this is that we can only do one thing at a time. This brain can only think one thought at a time. And that was really true of most computers, from the earliest computers until the mid-2000s. But even though these computers had this limitation for all of those years, they were still getting faster. Every 18 months to 2 years, they were getting twice as fast. You could run twice as many instructions in the same amount of time. What made it possible for these computers to get faster is something called Moore's Law. The little electrical circuits that you used to make the different parts of the CPU were getting smaller and smaller, and that meant that you could fit more and more of them on a single chip. With more of these building blocks, you can make these CPUs more powerful. And also, there was less distance for the electricity to flow between these different circuits, so they're able to work together faster. But of course, you can only make things so small, and there's only so much electricity that you can course through a circuit before it starts burning up. In the early 2000s, these limitations were becoming apparent. Chip manufacturers had to think, how are they going to keep making faster and faster chips? The answer that they came up with was splitting up this chip into more than one brain, basically making it possible to think more than one thought at the same time, in parallel. These separate brains that the CPU has are called cores. Now, when you hear people talk about a multi-core architecture, this is what they're talking about. Even though each one of these cores or brains is limited in how fast it can think, If you add more of them, they can do more in the same amount of time. But the thing is, in order to take advantage of this, you need to be able to split up the work that you have across the different cores. Unlike before, where these speedups were happening without programmers having to do anything, these speedups actually require programmers to change the way that they code. This is actually harder to do than you might think. Imagine that two of these cores need to work on the same bit of long-term memory. They both need to add something to it. Well, what number is going to end up in long-term memory after those two calculations? Who knows? It depends on the timing of when the instructions run on the different cores. So let's walk through an example of that. We'll start with the number 8 in long-term memory. Both cores need to add 1 to it, so our end result should be 10. Instructions have to use things that are in short-term memory, and each core has its own short-term memory. So let's say that the first core pulls 8 from long-term memory into short-term memory, and then it adds 1 to get 9, and then it replaces the value in long-term memory. So this means that the other core can now access the result of this calculation. So the long-term memory holds 9. The second core is going to pull 9 from long-term memory into short-term memory, add 1 to get 10, and then put that back into long-term memory. This means that our end result is 10, so all is well. But it wasn't guaranteed to end up this way. Let's see what happens when our instructions happen in a different order. So the first core pulls 8 from long-term memory. Then the second core pulls 8 from long-term memory, and you may already see what the problem is here. The first core will add 1 to get 9, then it writes 9 back to long-term memory. Then the second core adds 1 to get 9, and writes 9 back to long-term memory. So we end up with a result of 9, which is not what we wanted. This kind of bug is called a data race. When you have parallel code with shared memory, so two different cores that are working with the same part of long-term memory at the same time, you're very likely to have these data races. One way to get around this is to choose tasks that are independent of each other, so they don't need to share memory. Now let's go back to the Chrome and the content example that we were looking at before. You may remember that I said that these are all fairly independent of each other. That means that they're perfect for this kind of parallelism, where we don't actually need to share memory between them, and that's called coarse-grained parallelism. That's where you split up your program into some pretty large tasks. It's actually pretty straightforward to do this. You just need to figure out these large independent tasks, and Chrome did this from the beginning. The Chrome engineers saw that they were going to need to have some level of parallelism to be fast with these new architectures. Around the same time that Chrome was seeing this change in hardware, and seeing that if they wanted to have a fast browser, they were going to need to take advantage of this parallelism, we were seeing the same thing. We knew that we were going to have this coarse-grained parallelism in our browser too, if we were going to keep up. And we do now, although it took us a while to get there. It was a multi-year effort. We started testing our multi-process architecture in Firefox 48 with a small group of test users. But it wasn't until this past summer with Firefox 54 where we turned it on for all users. It took us a while to get there because we weren't starting fresh like Chrome was. We had a bit of a bumpier road. We were starting with this existing code base, which was developed before multi-core architectures were prevalent. And we needed to figure out how to break apart this code base without breaking things for our users in the process. So we needed to plan for that. But we didn't just stop at making plans for adding coarse-grained parallelism to the browser. We saw that we were going to need to take it further. Because when you have this kind of coarse-grained parallelism, there's a good chance you're still not making the best use of all of your cores, of all of your hardware. For example, you might have one tab that's doing a whole lot of work, but the others might not be doing much at all. That means that those other cores are sitting idle, so you're not getting the kind of speed up that you can from a parallel architecture. We saw that if we wanted to make a browser that was really fast, we couldn't just add this coarse-grained parallelism. We needed to add fine-grained parallelism too. So what is fine-grained parallelism? Well, that's when you take one of these big tasks and you split it up into smaller tasks. So these can be more easily split up across the different cores, across these different brains. But that does usually mean that you're going to have to share memory, as I was talking about before. And this opens you up to those data races. These data races are nearly impossible to avoid when you have shared memory, and they're incredibly tricky to debug. The thinking at that time was basically that to safely program in parallel, you need to have a wizard-level understanding of your language. One of the distinguished engineers at Mozilla actually put a sign about 8 feet high saying, "You must be this tall in order to write multi-threaded code." Now, of course, when you have a project like an open source browser where you have thousands of contributors, all at different skill levels contributing to the code base, you can't code in a way that requires a wizard-level understanding of the language. If you do, you're going to run into these data races for sure. And these data races and other memory bugs cause some of the worst security issues in browsers. So if we wanted to take advantage of this fine-grained parallelism without the peril that data races introduce, we had to find a way to make it safe. So rather than starting a project to rewrite the browser, we started sponsoring a project to create a new language to write this browser in. This language is the Rust programming language. As part of its design, it makes sure that these kinds of data races just don't happen. If you have code that would result in these kinds of data races, it won't compile. We started sponsoring work on Rust in 2009 or 2010, and it wasn't until about 2013 that we actually started putting it to use for a browser, though, to see if it could actually create the kind of browser that we wanted. I don't know if you've heard of the term yak shaving, where you have to do one seemingly unrelated task before you get to work on the thing that you actually meant to. Well, at Mozilla, we have some pretty big yaks to shave. So in 2013, with this language in hand that allowed us to code in parallel without fear, we started looking at how we could really introduce fine-grained parallelism into the browser. The project that we started to do this is called Servo. It started by looking at this rendering engine pipeline and asking, what if we parallelize all the things? So this means that we're not just sending the different content windows with different pages to different cores. We're taking a single content window and splitting up the different parts of it. This means that if you have a site like Pinterest, each different pinned item can be processed separately from the others. So for example, for CSS, you could send each pinned item to get its CSS filled out by a different core. This means that you can speed up different parts of the rendering pipeline by however many cores you have, which means that as chip manufacturers add more and more cores into the future, these pages are going to get faster and faster. This is the key. This is why this fine-grained parallelism is so important. This is why we spent so much time and risked so much in pursuing it, because it wasn't clear at the start that this was actually going to work. Coarse-grained parallelism is pretty straightforward, but this fine-grained parallelism, creating a language that would support it safely and then implementing a browser that used it, that was a tough research problem. But the time and effort has paid off. We found out that these ideas work really, really well. Over the past year, we started bringing pieces of this over to Firefox. We're doing this as part of Project Quantum, which is a major speed up of Firefox that we've been working on for the past year. It's been kind of like replacing the parts of a jet engine mid-flight. And we actually had our first release of Firefox Quantum in November. One thing that we brought over is our parallel style engine called Stylo. That splits up all of the CSS processing across the different CPU cores, as I mentioned before. It uses a technique called work stealing to do this. Whenever the core runs out of work, it can steal work from the other cores. So this makes splitting up the work efficient. And it makes it possible to speed up CSS style computation by however many CPU cores you have. Another piece that we're bringing over is called WebRender. WebRender takes the paint and composite stages and combines them together into a single rendering stage. It uses the hardware in a smart way to make painting the pixels faster, which means it can keep up with those larger displays. To do this, it uses another highly parallelized part of the computer which is specifically meant for graphics. This is called the GPU, or the graphics processing unit. The cores on the GPU are different from the cores on the CPU. So on the CPU, you have 2 or 4 or 6 cores. On the GPU, you'd have hundreds or thousands of cores, but they can't do things independently. They have to all be working on the same thing at the same time. You need to do a lot of planning if you want to maximize the amount of work that they can do at the same time, and that's what WebRender does. With WebRender, we can get rid of the performance cliffs that trip up web developers. So for example, if you animate background color right now, it can make your animations start and stop. It can make it look janky, because the paint and composite phase have too much work to do. Because of this, there are currently a lot of rules about what you should and shouldn't animate. We're going to be able to get rid of a lot of these rules, so web developers don't need to hack around these performance cliffs. We can take pages that render in Chrome and in the previous version of Firefox at 15 frames per second today, and bring them up to maximum FPS, whether that's 60 or 120 frames per second. But it's not just the browser's own code that needs to run faster. The browser's also going to need to run application code faster. So what I'm talking about here is things like JavaScript. The JavaScript engine is a part of the browser that I haven't talked about yet, so let's see where that fits in. JavaScript gives you a way to change the document object model. So that's the thing that you built up during the parsing stage. When you change it, it triggers the creation of a new version of the page through this rendering pipeline. A lot of sites these days are pretty JavaScript heavy. That's where they spend a lot of the time they have, a lot of the 16 milliseconds that they have to figure out what a page should look like. These sites are using frameworks like React, which does a lot of calculations in JavaScript to figure out what it needs to change in the DOM tree. Now, browsers can make the JavaScript engines that run this JavaScript faster. But JavaScript really isn't designed for machines to run it quickly. It's designed to be easy for humans to write. The way that JS engines get fast is by making guesses about where the JS engine can take shortcuts with your code. But sometimes those shortcuts don't work for your code. And there's only so many shortcuts that they can bake into the JavaScript engine. Which means that there's only so much that JavaScript engines can do to speed up the application code. But what if application code could run in parallel? What if it could take advantage of these multiple cores in the same way that the browser's own code is doing? Over the past few years, browsers have been adding features that make this possible. One that you may have heard of is web workers, which have been in browsers for a few years now. These allow you to have JS code which runs on different cores. You may also have heard of shared array buffers, which started landing in browsers this past summer. Now, unfortunately, because of the Spectre bug that happened a few weeks ago, which you may have heard of, shared array buffers had to be turned off. But we're hopeful that we can turn them on again soon. So what shared array buffers do is give you that shared memory that I was talking about before, which you need for speed a lot of times when you're working with fine-grained parallelism. But like I talked about before, it's pretty tricky to actually manage that shared memory on your own. And web workers can be hard to use themselves. That's why so few sites and applications use them today, even though they've been around for years. It would be nice to have a language like Rust, which gives you those guarantees that you're not going to have data races, and which makes it easy to split up the work across different cores, across these different workers. Well, there's actually another standard that started landing in browsers last year that helps with that. WebAssembly makes it possible to run other languages besides just JavaScript in the browser or in Node. Now, it doesn't quite have access to the DOM yet. The working group is working on that. And they're very close to finishing the work on threading, which makes it possible to work across the different cores. There are also other things about WebAssembly that help application performance. It was designed for machines to run it fast, not to be easy for humans to write. Because developers usually don't have to write WebAssembly directly. Instead, they're usually writing in another language like C or C++ or Rust. And that means that WebAssembly doesn't have to be easily readable for programmers, so that the engine doesn't have to do that guesswork that it does with JavaScript. This speed of WebAssembly, even without threading, is what's making it possible to run PC games in browsers today. So these standards, web workers and shared array buffer and WebAssembly, make it possible for applications to take advantage of parallelism too. For example, in a framework like React, you could write the core algorithm in parallel. And that way, the work to figure out the changes between the previous version of the app and the next version can be distributed across all of the different cores. And Ember is already starting to experiment with WebAssembly in their Glimmer VM, which may be able to take advantage of this parallelism in the same way too. I think we're going to see a big shift towards using these standards in frameworks over the next few years. So let's get back to this challenge that we had. Here are the pieces of this puzzle. Here's how we can address the challenge. This is what browsers need to do to support the new devices and the new applications that are coming to the web. There's the coarse-grained parallelism of splitting the different content windows in the Chrome among different processes. There's the fine-grained parallelism of splitting up the work of a single web page so that it can be distributed across the different cores. And then there's enabling application code to be parallelized as well. The coarse-grained parallelism is already there in all of the browsers. Chrome was the first to do this, but pretty much all of the browsers have caught up at this point. Enabling application code to go parallel, that's something that's happening in standards bodies and is being adopted by all of the major browsers. It's this fine-grained parallelism that's still a question mark. This is where most browsers have done the least so far. And it's actually not clear how to do it in most browsers, because the C++ that most browsers are written in is actually pretty hard to parallelize in this way. But I think that all of the browsers are going to need to do it. We may be the first browser together. We may be the first browser to see the speed-ups of this fine-grained parallelism. But we really want all of the browsers to get there with us, because that's the way that we're going to keep the web going. That's how we're going to keep it healthy and vibrant, no matter how much the browser's limits are pushed. Thank you all for having me, and thanks for listening.